Let's look on the second derivative test for the relative maximum and relative minimum, and it happens to be very useful in some cases. So assume that we have a function so that f prime at point C is exactly 0. So this assumption says that x equals C is a critical point. Then we also assume that second derivative exists around x equals C. So then if second derivative is negative at point C, then f of x has a relative maximum. How could that happen? Well, if second derivative is negative, then the function is concave down. So that's how the graph of concave down function look like. Okay, and if we know that we're looking on a critical point on this place, that's the thing. And that is the relative maximum. Likewise, if we know that second derivative is positive, so the graph will look like this. And we are at a critical point, then it is a relative minimum. So here is x equals C, where the first derivative is 0, and that's exactly relative minimum. The downside of this, if second derivative is exactly 0 at a point, then the test fails, and we know nothing as far as this test goes about what happens at x equals C, and we need to use other tests to determine what happens at this point. As was mentioned before, a second derivative test might fail. This is one of the examples where it fails. We consider the function f of x being x cubed. Its derivative is 3x squared and second derivative is 6x. We can find all the critical points of this function, set the derivative equal to 0. It's 3x squared equals 0. That gives us x equals 0 as the only critical point. And at this point, the second derivative at x equals 0 is 6 times 0, 0. Now the second derivative test is inconclusive, or it fails. But on top of that, we know that the function x cubed is increasing for all x, and we can actually see the graph of this function, which goes like this. So there is no critical point at x equals 0. That's one situation when this graph, when this second derivative might fail. Second derivative test might fail. And this is another situation when the second derivative test fails as well. So we look on the function x to the fourth. First derivative is 4x cubed and second derivative is 12x squared. Then again, the only critical point is x equals 0, and the second derivative at that point is 0 as well. So the second derivative fails. Second derivative test fails. But what we know that this function, well, this should be x to the fourth here. So let me go to the graph of this function, like this. The graph of x to the fourth is this u-shape, which is flattened out. And the point is that x equals 0, is a relative minimum. But the second derivative test fails at x equals 0, as we just calculated. So it's true that second derivative test might fail at a relative minimum or maybe relative maximum, or it might fail at some other place. Let's work on an example where we use second derivative test. So we look on this function, x to the fourth minus 4x cubed plus 2, and we'd like to know if it has any relative maxima and minima, and we're going to use exactly second derivative test to determine if possible. So first of all, we find first derivative and any critical points. So first derivative will be 4x cubed minus 12x squared. Since, well, we set derivative equal to 0 and solve for x, we get 4x cubed minus 12x squared equals 0. Factor out 4x squared, there is x minus 3 left. So we get 4x squared is equal to 0 and x minus 3 equals 0. So the first equation gives us x equals 0, the second equation gives us x equals 3. And now we look on the first derivative. It is defined everywhere, it is a polynomial. So there are no critical points of second kind where the derivative is not defined. So to use second derivative test, we need to find second derivative. And that's the derivative of 4x cubed minus 12x squared. This is 12x squared minus 24x. And we test the critical points. We set x equals 0 into the second derivative, and we get 12 times 0 squared. There is a multiplication sign here. Minus 24 times 0. And it works out to be 0. So if second derivative 0, we don't know anything about concavity, so the test fails at this point. At x equals 3, we get that second derivative at 3 is equal to 12 times 3 squared minus 24 times 3. That's 36. That makes the function to be concave up around that point. And if the function is concave up, it looks like this. And we are at a critical point, so this must be relative minimum. So the second derivative test gives us an answer at least at one place. So we have that test failed at x equals 0, and f of x has relative minimum at x equals 3. Okay, once we completed the second derivative test and figured out that it fails at x equals 0, and there is something that we can definitely say at x equals 3 we have a minimum, we can continue working and actually get a definite answer. So I'll copy the derivative, and we'll use first derivative test to investigate what happens at x equals 0. So remember, the critical points of this function are x equals 0 and x equals 3. So those are our intervals. We're going to choose some test points. So to the left of 0 there is a test point -1. Between 0 and 3 we can choose test point x equals 1, and to the right of 3 there is x equals 4, a good test point. Then calculate values of the derivative at all of those test points. We get at -1 we get -16. At +1 we get -8, and at +4 we get +64. Tells us that derivative on each of those intervals will be negative, negative, and positive. So it's going to be negative to the left of 0. It's going to be negative from 0 to 3, and then it's going to be positive to the right of 3. Then our conclusion is that since the derivative is negative both to the left and to the right of 0, f of x has no maximum or minimum at 0. And then at x equals 3 we knew that the function has the relative minimum, and this first derivative test confirms what happens at that point. Now let's work on another example of second derivative test. So we have this function cosine x minus x for x between 0 and pi, between 0 and 4 pi. And we'd like to find any relative maximum or minima if possible. So find first derivative, which is derivative of cosine x minus x, that's negative sine x minus 1. Since this derivative is defined for all x, we just have to solve derivative equals 0 to find critical points. We get negative sine x minus 1 is equal to 0. So negative sine x is equal to 1, or sine x is equal to -1. And all solutions of this equation are x equals negative pi over 2 plus 2 pi n, for any n being an integer. But in this problem we need only points between 0 and 4 pi, so we can easily see that for n being exactly equal to 1, we get 3 pi over 2, and if n is exactly equal to 2, we get 7 pi over 2. Those are two critical points that we have. And once we have those critical points, we look for the second derivative. That's the derivative of negative sine x minus 1. That's negative cosine x. And we test those critical points. At x equals 3 pi over 2, we get that second derivative. At 3 pi over 2 is negative cosine of 3 pi over 2. That's negative 0, which is 0. And the test fails. At another critical point, we get a similar story. A second derivative at 7 pi over 2, it's negative cosine of 7 pi over 2, that's 0 as well. So test fails at both of those points. And we pretty much don't know anything about those critical points if we don't use anything else in this problem. Okay, once we completed this work on using second derivative test, we ended up with no answer. So I guess we can continue working and use the third derivative test on this function and see what is actually going on there. So I'll copy the value of the derivative, and there are two critical points between 0 and 4 pi. There is 3 pi over 2 and 7 pi over 2. Then I will use the third derivative test to figure out what happens at critical points. What we can do, we can say, well, we can note that for any value of x, sine x will be between negative 1 and positive 1. Then we can multiply all the way by negative, so we're going to get 1 is greater or equal than negative sine x, greater or equal than negative 1. So we multiply it all the way by negative 1. When we multiply by a negative, inequality signs reverse. And then what we're going to do, we're going to subtract 1 from each term. And as soon as we subtract that, we arrive at 0, negative sine x minus 1, and negative 2 in all the places. So what it says that our derivative, which is exactly negative sine x minus 1, will be always less or equal than 0. That's the part that is useful to us. And since the derivative is negative in most places, we can see that on all the intervals between 0 and 4 pi, the derivative is negative, and the function will be decreasing. Since the function is decreasing everywhere, there are no relative maxima, there are no relative minima for this function. So our conclusion is that the function has actually no relative maximum and no relative minimum on the interval from 0 to 4 pi. And then after that we can look on this function on the graph of this function, and we see that this function just keeps going, keeps decreasing and decreasing and decreasing.